Hi everyone, welcome
Just
to
going to
this
have a look
video.
at worked example
Today we're going to have a
14.
look
So
at
particle
what's called
moving in a straight
kinematics.
line,
So
such that its
kinematics is
displacement from the
basically the
origin
study
at
of
time is
motion of a
modeled by
particle
the
without actually
equation.
considering the cause of the motion.
And I'm just going to
When we talk
copy
about
that.
kinematics, there's really three things we look for. What we talk about is displacement,
So part A
velocity, and
says identify
acceleration,
the initial
and
position.
they're all linked
So we're
together,
talking about
as we'll find
displacement in
out
terms of
later on.
time, t.
When we talk
So
about
t
displacement, it's
is
usually
time.
denoted by
Initial
x. For velocity,
means
just
where are
v,
we
and acceleration
before we
is
start
a.
moving, basically. So
So that's what the
we're
notation for
finding
each of those. Displacement is the
x
position of a
when
particle,
our time
specifying both
is
distance
basically
and
0.
direction.
It's before we start.
So
So we're
basically,
just
it's
using
just
t
the
equals 0.
position.
Right, work that out. We get x is actually
And
minus
displacement's
12.
probably
Just
one of the
means that we're
most
12
common
units to the left of the
parts of
origin.
this.
Just remember that for our
For
negative sign.
velocity, v, it measures the rate of change
Part
of
B says
displacement.
obtain the velocity and hence state the initial velocity and describe its initial motion. So what
So
that's talking about,
the
if we rate of change of the displacement, if our displacement is x, the rate of
its
change we're
velocity,
talking about
if we
the
remember,
derivative,
v
so it's
is
actually the
actually
same as dx dt.
the
If we
derivative of
find the
x,
derivative
and
of the original
we're talking
function,
about t in terms of time. So I'll just put a note up the top.
okay, so
Okay, when we
our
say t,
derivative is going to be
most of these
2t
fall
take
into
4
under time. So
how
that's our
fast are we
velocity,
going?
rate of change of displacement. So how far are we
Hence
going?
states initial
So
velocity.
kilometers per hour, or
So
it's our distance over time.
so I'll
Acceleration
write
at
is the
time
last one is
t
going to be
equals the
0 for
average.
initial.
Sorry, the rate of change of velocity.
We
So
get
rate
v
of
equals minus
change
4
for
velocity,
so describe its initial
and
velocity.
essentially it's the same thing
So
as
at t
um,
equals 0, our
the
initial
displacement. So
velocity is
the rate of
negative,
change is going to be
meaning that
the
we
v
are
dt.
to the left
So
of the
for v,
origin. We've got dx dt,
for a, we've
so we're
got the
moving
v dt.
left of the origin. Just as a side note, something to take further, if we know dv dt is a, and actually no, forget about that. That's going to confuse you. So
Okay,
displacement,
v is
velocity,
less than 0,
acceleration,
so we're moving
three
to the
things we're
left.
looking at. When we look at displacement,
Part
commonly
C says
used
to what time and position
conventions
is
for
the
motion along
particle
a horizontal straight line.
momentarily at
So we've got
rest.
either x is greater than 0,
So
x
at
less than
rest,
0, or x equal to 0. So this is the talking about how far away from the origin.
we're
Okay,
finding the
if x is
velocity
greater than 0,
when v is, or the
that
time when
means
v
that the
equals 0,
particle, um, meaning that it's stationary, is to the right. Yeah, so our velocity was 2t take 4, so we're solving that when it's 0.
Okay, so positive, meaning
So if you work
particle
that
is to
out,
the
we get
right of
t
the
equals
origin, 2.
and if it's less than 0 or negative,
So
the
it's going to
position
be the same thing, but we're going to be to the left
of that
of
is when we
origin.
find um, if it's equal to 0, it is
Using
at
our the origin
x function. We just sub in t equals 2. Alright, so what we're talking about
or
is
if
take 8, take 12, so x
we
is
have
actually
x equal minus 10
minus
on a straight line.
16. So
Our
the
origin is
particle is
here at
momentarily
minus
at
10
rest after
here,
2 seconds
so we're
at the
sitting
position
to the
16
left of the
meters
origin.
to the left of
It's
the
also
origin.
important to note this distance here at minus 10 is going to be the same as if we looked to the positive of the origin. So
It's just
part
talking
D
about
says show that the
are
particle
we
is
to the
at the
left or to
origin
the
when
right
t equals
positioning
6
is what
and
that
calculate the distance
symbol
it has
there
travelled to reach
positive or
the
negative.
origin. So
As
when
x equals 0 means we're sitting at this spot here. Oops, t equals 6. Velocity, very similar to acceleration, a positive, a particle moving in a horizontal line. So the sign of the velocity indicates that if it's greater than zero, we're
Okay,
moving.
we get
Now we're
x
moving
equals 0 to
so the particle
the
is at the origin when
right.
t equals 6.
The
If it's
motion
less
of the
than 0 or
particle for the
negative,
first
we're
6
moving to the
seconds is
left, going to be. And if it's equal to 0, we're not moving or is stationary. So we've got our origin. We started at minus 12. That's from part A, when t equals 0. At t
average
equals 2,
velocity.
slightly different.
We
So it's the rate
found
of
it was
change of the
minus
displacement
16,
measured by the gradient of the chord
and then
measuring 2 points on a position time graph. So if we were to graph a function f of x, and it might be
and then we turn
um,
back
around and end
quadratic,
up back at the origin
and this is
at
our
t equals
distance
6.
so that's
And
describing
time. So our distance varies depending on the
the path that
time.
it's taken.
This is our graph, and we want to find the rate of change um, of the displacement. So we're
So
looking
the
at
total
the distance between, it
distance that
might
we've
be,
travelled
is the
3
distance between
and
minus
4,
12 and 16.
sorry,
So we'd plot those 2 points
which
and we'd
is
find the
4,
distance,
and then
find the rate
the
of
total
change of that.
distance there, which is 16.
So
So
that's essentially what we're
4
doing. So it
plus
requires
16 gives us
coordinate
20.
geometry. We can't
So
use
the
calculus.
particle has travelled
And to find
20
those,
metres.
we can just use our straight line, um, calculate the average speed over the
Average
first 6
velocity.
seconds. So average
So the
speed, change in displacement, well, it's going to be our y2 take y1. In this case, it's x2 take x1 because that's our y values.
if you remember back is
Usually we
distance
have
over
y
time
we
against
found
x. We've
that
got
our
x
total
against t.
distance was 20. So instead of
And
x,
the
we're going to have
time for that was
t2
6.
take
So working that out
t1.
is about 3.5.
So that's how we would find the average velocity.
Uh,
And we're talking about speed, so it's meters per second. Last thing,
and the last bit was
acceleration.
calculate the
As we
average
said from the
velocity
first slide,
over
we've got
the
the
first
three.
6 seconds.
So
Average velocity
kinematic
is the
information
rate of
X, B,
displacement.
and A connecting each other. Um, and as we had a look at before, we find V by finding dx dt, and we find A by finding
Okay, our
the
first
derivative of
position
V.
was at 0, minus 12.
So
That was our
acceleration
initial.
measures the rate of change of the velocity. Usually we denote that by meters per second squared. Second point we had was at t equals 6 and 0, can sometimes be written
That's
as
where we end up.
ms to the minus 2. It's just notation, whereas velocity usually is meters per second. So x2 take x1, we get 0
And
take
for
minus 12 over displacement
t2,
or the
which was
distance,
6,
usually
take 0, we get positive 12
kilometers
over
or
6, which is
meters.
2.
Okay, and I'm going to leave it there. So that's it for